Hello friends, so this is part 4 for the year 2021, and in the part 4 we are going to solve 7 questions, and all these 7 questions are from the mains. So only thing that is left from this 2021 are the advanced question, which will be covering in the part 5 rather, not 5th. So in the first question, it states that a ball having a charge to mass 8 microcoulomb per gram is placed at a distance of 10 centimeter from a wall. Suddenly, an electric field 100 Newton per meter is switched on. Assuming collision to be elastic, find the time period of the oscillation. So basic figure is given to us. We have body and it is moving towards the wall, and the electric field is switched on. So obviously there will be a force because of this electric field, and that is going to provide the required acceleration to the body. And we are given that charge to mass ratio is given to us, that is Q by M is given to us as 8 microcoulomb per gram. So let's start with the force on the body, or we can say it's a ball. So you can say force on the ball due to electric field let us call that force as F E, which will be equal to Q multiplied by electric field, and this force is going to provide the required acceleration for the body. So we can write this as M multiplied by A will be equal to Q divided by multiplied by E. So from here we can say our acceleration A will be equal to Q upon M multiplied by E. Q upon M is given to us as 8 microcoulomb per gram. And from here we can calculate our acceleration. So we substitute the value, we get our acceleration is equal to, we are given 8 microcoulomb, 8 into 10 to the power minus 6. Electric field is given to us as 100. And this is per gram. So this will be multiplied by 10 to the power 3, that will be now kg. And we have our electric field, which is our 100 Newton per meter. Therefore we get this as 8 into 10 to the power minus 3 multiplied by 100. Therefore we can say that it will be equal to 0.8 meter per second square. Now we can use simple equation of kinetic and find out the time. Suppose in one direction the body takes a time t to reach the wall, okay, and we have to keep in mind that the collision is perfect elastic. So we can find out this time t. Distance we know is our given to us as 10 meter. So we can say using kinematics equation, we can write S is equal to ut plus half et square, and initially is at rest, so our u will be equal to 0, Therefore we can write S is given to us as 10, or let us simplify it first. We can write our S, U will be 0, so this comes as half a t square, and from here we get our t square is equal to 2 times S divided by A. So this comes as 2 multiplied by 0.1, and this is about 0.8, which gives us 0.8, 0.1, 1 by 4, giving us 0.25. Therefore, we can say that our t will be equal to 0.5 seconds. But this time t is for one direction. We have to find out the time period of the oscillation, which means it should be coming back to the starting point, and the collision is perfect. So therefore we can say that the time return to the original position should be the time taken to reach the wall. Therefore we can say that collision is elastic. Let us call this original position as A, final position at B. Therefore we can say time from A to B, that time from A to B should be equal to time from B to A. And let us say this is equal to T, or T prime rather, okay, because T we already know. Let us call this as capital T. Capital T. So we can say from here the time period of oscillation will be equal to 2 times small t, which gives us that this capital T is equal to 2t, which is 2 multiplied by 0.5, giving us 1 second. Therefore option number B is correct. Option B is correct. Next question. We are given a certain charge Q is divided into two parts, Q and capital Q minus small q. How should be the charges Q and capital Q be divided so that small q and capital Q minus q placed at a certain distance apart experience maximum electrostatic repulsion? So here we are given that we have a charge Q, capital Q. It is divided into two parts. One is given as small q, other one is given as capital Q minus small q. And let us assume that the distance between the two is our r. So we have to find out this value of r such that they are at maximum electrostatic repulsion, or we can say the force of electrostatic force should be maximum. So we can just directly write the formula for the electrostatic force. We can say electrostatic force, that is at F, will be equal to K multiplied by small q and capital Q minus small q divided by r square. And we want that F should be maximum. Okay. So we can say that to maximize F, we need to maximize the function, let us represent that as a small f of q is equal to q capital Q minus small q. And in order to maximize this is our standard quadratic. So let me write it. We can write f of q will be equal to small q multiplied by capital Q minus q square. And in order to maximize it, we are going to find out its derivative and substitute that derivative is equal to 0, equate its derivative equal to 0. So we derivate it df of q upon dq will be giving us q minus 2q, equating equal to 0. This gives us that small q is equal to capital Q divided by 2. So it is divided into 2 charge. So we found out value of this first one, which came as capital Q divided by 2, and we can easily find out the second one, which is Q minus Q by 2. So we can say that second is our Q minus Q. This will be Q minus capital Q by 2, giving us Q by 2. So it means the charges should be equally divided. Okay, so from here we can say that the charge capital Q should be equally divided. So it means it will be Q by 2 and other will be also Q by 2. So option A is correct. A is correct. Next question. We are given an electric dipole is placed on x-axis in proximity to a line charge of linear charge density 3 into 10 to the power minus 6 coulomb per meter. Line charge is placed on the z-axis and positive and negative charges of dipole is at a distance of 10 millimeter and 12 millimeter from the origin respectively. If a total force of 4 Newton is exerted on the dipole, find out the amount of positive or negative charge on the dipole. So we can just draw an approximate figure. We are given that we have a dipole which is placed on x-axis and line charge is placed along z-axis. So let us suppose we have line charge and density is positive, and suppose this is our x-axis and we have dipole which is placed along this x-axis such that our positive is at 10 millimeter. So this is our plus q and this is our minus q. And we assume that the length of this dipole is supposed to be x, and let me write it other way. So we are given that positive is at a distance of 10 millimeter. Okay, so this distance is about 10 millimeter and negative of the dipole is at a distance of 12 millimeter. Therefore, the distance between the charges of the dipole will be over 2 millimeter. Okay. And this is line charge. Let us suppose its charge density is given as lambda. So lambda is given to us, so we can write that charge density, line charge density, which is our lambda, is equal to 3 into 10 to the power minus 6 coulomb per meter, and dipole is along x-axis. So this is our positive x-axis, and this is our z-axis. So you can say for dipole, placed along x-axis, and we can write that positive charge is at a distance, positive charge is at a distance, let us call this as x positive. This is at 10 millimeter, which will be our 0.01 meters. Similarly, we can write negative charge is at a distance, let us call this as x negative, which is given as 12 millimeter, which will be equal to our 0.012 meters. And net force of the dipole is given to us as 4 Newton. Net force on the dipole is, let us suppose F is given as 4 Newton. And we are going to calculate what will be the actual net force and equate that net force equal to calculated net force to the given net force, which is 4 Newton, and from there we can easily find out the positive or negative charge, whatever there it is, because charge will be same. So first of all, we are going to find out the electric field, and electric field we can just convert into the, you can say, the force. So we can say electric field due to line charge electric field due to line charge, and suppose that is our E, which will be equal to our lambda divided by 2 epsilon naught multiplied by R. And we have two different distances, x positive and x negative. So let's find out the force on each charge. Force on each charge. First one is our positive charge. Let us call this as force as F positive, which will be equal to Q multiplied by electric field at the positive charge, and we get this as our Q lambda upon 2 pi epsilon naught, and distance is our 0.01. And we find out for negative charge. Let us suppose that is our F negative will be equal to charge multiplied by the electric field at the negative, which comes as Q lambda, and this is our 2 pi epsilon naught, and distance is 0.012, and this is negative, so this will be our negative. Therefore, now we can easily write the net force. on the dipole. Net force on the dipole, let us call this as F. That will be equal to our F positive plus F negative. And please remember, this negative is just representation of the direction, that it will be in opposite side. Okay. And therefore we get our F is equal to, we can take this as Q lambda upon 2 pi epsilon naught as common, and we get this as 1 upon 0.1 minus 1 upon 0.012. And we are supposed to find out Q. So let us substitute our value, and this will be giving us Q times okay, let me write it. It's quite big number, 898, 400. But we are given this F as 4 net force, so we can say our 4 is equal to Q times 898, 400, which gives us that a Q is equal to 4 divided by 898, and this is 400, which gives us approximately 4.45 into 10 to the power minus 6 coulombs. So option number D is correct. Option D is correct. Next question. We are given what will be the magnitude of electric field at point O as shown in the figure. Each side of the figure is L and the perpendicular to each other. Basic figure is given to us, which is just a square, but these 4 sides missing. So if we join them completely, we are going to get some kind of square, which total length will be there 2L. Okay. And we have to find out the electric field at the origin, at point O, and for various value of charges which are placed at all the vertices. Okay. And here we have to remember that suppose we have a plus Q charge, and then the electric field at a distance of r will be given as E is equal to KQ upon r square, and the direction of electric field will be away from the charge. And if we are having a negative charge, then in this case at a distance r, the magnitude of electric field will be same, but the direction will be towards the negative charge. Okay, so we have to remember this particular thing. So let us draw the figure, and so this is the basic one, and charges are our minus Q, plus Q, and here we have plus 2Q, plus Q, and this is also over plus 2q minus q plus q, and this is over plus 2q. And for the electric field, we have to find out the distance between the point, which is given as O, and the respective charges. So we can just simply join all these points. This will be giving us distance, and the length of the side it is given as L. Okay, so we are given this is L and this is as well L. So we can easily find out that the distance between, suppose this is our A and we are having this as B, then we are having this is C, D, and this is our E, F, G and H. So we can see our AO will be equal to L times square root of 2. Similarly, it will be also L times square root of 2, L times square root of 2, and we are having here L times square root of 2. And we can just draw the respective electric fields, only electric fields, and we have our charge that is a center O, and we have our point A. Point A is our negative, so therefore the direction of electric field of this point A will be over EA in the direction of the charge, which is our negative. And second point is our B, and this B is having our plus Q, so therefore its direction will be away from it, so this will be our EB. And next is our point C. So point C is our positive, so therefore electric field of this point C is plus 2q, and that will be away from the charge, which will be our EC. Next point is our D, and D is lying along the diagonal, and its direction of electric field, it is also plus q, so it will be along, this will be our ED. So this point is our D. Then it is our E, so E is somewhere here, and it is plus 2q, so the electric field is our, so this will be our EE. Similarly, we can write for the our F is positive, so it is going to have other direction, that is our E of F. And we have our, one second, plus plus, minus is along A, and only minus is along A and H. Okay, and so this is going to give us E of H, and this point is H. And finally we are having, this is our point G, and electric field will be in the opposite direction, that is our E of G. Therefore, let me draw only the electric field. It's a little bit confusing. So electric field, so this is point O, and we are having this will be over EA, and EG, and this will be over ED, EE, EF, EB, EC, and this is our EH. Okay, now let's find out so here we have to remember that point A is here and point B, this is point E, this is our F, H, G, and this is our D, and this is our E. Except this EH and EA, these two are negative charge. This is minus Q and this is also minus Q. All the charges are positive, so the electric field will be entirely in the opposite direction of the respective charges. Now let's find out what will be the electric field because of EA and everything. So we can say that our electric field because of EA will be equal to, this comes as KQ, and the distance is square root of 2L whole square. And next we can find out our EB. EB is equal to KQ L square. EC will be equal to 2KQ upon L square. And we have ABC, then we can write our D will be equal to KQ square root of 2 L square, and we have ABCDE will be equal to 2KQ upon square root of L whole square, and we have then E of F will be equal to KQ upon L square, and we are left with F, G and H. E of G will be equal to 2KQ, and we have this is L square, and E of H is equal to KQ 2L square root of this. So these are the respective electric fields. And now we have to remember that now we have to see how the electric field is going to behave. So first of all, from the figure itself we can see that electric field because of the H and electric field because of the A, they both are in opposite direction. So this is our EA and we are having EH. They are both opposite direction and their magnitude is same. Okay, so we have EA and we are having EH. So both are same but opposite in direction. So we can say electric field EA plus electric field EH will be equal to 0. So these two are going to balance out each other. And then we are left with rest of the electric fields, and let's find out what will be now the net electric field. Okay, so EA and EH balance out each other, so we are left with the rest of the electric fields. So let me draw that figure once again. And and 2Q, okay, So first is our, this is B, and this is point G, and at B we are having a charge of plus Q, and H we are having a charge, sorry, G we are having charge of plus 2Q. So this is our plus Q and this is our plus 2Q. So obviously we can just say from here that the electric field due to point G will be higher as compared to the electric field due to B. So from here we can say that, let me write it here, our electric field G is greater than electric field at B. Therefore we can draw that the net electric field because of this EG and EB will be towards the left side. So this is our net electric field, which will be our EG minus EB. Okay. So we can find out our EG minus EB, and EG is our 2kq upon L square minus EB is our kq upon L square. So this gives us kq upon L square. So the net electric field because of this EG and EB will be our kq upon L square. Next is our point E and D. So this is point E and this is point D. E is having plus 2q and D is having plus q. So therefore the magnitude of the electric field because of this charge at E will be in the higher side as compared to because of D. Therefore we can write that our electric field at E is greater than the electric field of our D. So net electric field will be towards our D. So this is our net electric field towards point D and this is point B. And its magnitude will be our electric field of E minus electric field of D. So we can find out electric field of E. It is our electric field of E 2kq, 2kq, and we have this as 2L square minus electric field D is kq and we have this as 2L square, and this gives us equal to, we have this as kq upon 2L square. So this comes as kq upon 2L square. And then we are left with 2 points. These are our C and F. So this is our point C and this is point F. And C and F, C is having plus 2q, and so we have this as plus 2q, and F is having plus q. Therefore the magnitude of the electric field because of C will be greater than the magnitude of the electric field because of F. Therefore we can say the electric field due to C is greater than electric field due to F. So the net electric field will be towards point F, and its magnitude will be electric field C minus electric field F. C and F, yeah. So C is our 2kqL square and F is kqL square. So we can say our EC minus EF is equal to 2kq upon L square minus kqL square, which gives us kqL square. So from here we get it is equal to kq upon L square. And let me draw this cleanly. So we have this 3 electric fields, and this difference of EGB, let me call this as EGB, and let me call this as EED, and finally let us call this as ECF. So this is our ECF, and we are having this as point O, and this is our ED, and this is our EBG, and their magnitudes are kq upon L square, and here also we have kq upon 2L square, and this is our kq upon L square. So we have 2 electric fields, EBG and ECF, both are at a 90 degree, so therefore we can find out their resultant. And let us suppose their resultant is given as E, or rather we can say E prime. So we can say our E prime will be equal to cos 90 will be 0, so we can just write directly this will be our EBG whole square plus ECF whole square and its square root, and both are equal. This is kqL square and this is also kqL square, so we can write this as twice multiplied by kqL square and its square root. And whole square. So this gives us kq L square and square root of 2. So finally we found out 2 electric fields, and both are opposite to each other. This is our EAD. Magnitude is kq upon L square, and this comes as kq L square multiplied by 2. So both are directly opposite. We can just find out the net electric field directly. So we can say net field, let us call that our E, will be equal to our E prime minus EED. So E prime is our kq L square square root of 2 minus kq L square, and we can just take common. We get this as kq upon L square is equal to square root of 2 minus 1. So this is our net electric field at point 0. This is point O, not 0. Okay, so the option number B is correct. Once again, they are not perfect match. Okay. One second, I will sort it out. EED, it is 2. Yeah, my mistake. I copied it wrong. This is 2. This is also 2. So this comes as 1 by 2. And we get this as KQ 2L square. This is 2 root 2 minus 1. Okay, any other difference? Okay, they are inside the square, so we can just modify it. Answer is more or less correct. We can substitute value of K, that is 1 upon 4 pi epsilon naught. This comes as Q upon square root of 2 whole square, and this comes as 2 root 2 minus 1. Okay, now option B is correct. Yeah. One second, I made a mistake. This is our 2 root 2. Yeah, this looks good. What the problem is there? It's not whole square. My mistake. I read it wrong. So this is our simple 2L square. So option B is correct. Next question. We are given the total charge enclosed in an incremental volume 2 into 10 to the power minus 9 meter cube located at the origin is dash nanocoulomb. If the electric flux density of its field is found as d e raised to the power minus x sine of y I unit vector minus e raised to the power minus x cos of y j unit vector plus 2z k unit vector coulomb per meter square. So we are given that electric flux density is given. So we can use the formula between the electric field and electric flux density. So we know that electric flux density, that is our D, is equal to epsilon naught times our electric field. So from here we can say that our electric field is equal to 1 upon epsilon naught and our electric flux density. And this electric flux density is given to us. Okay. So we are given electric flux density is equal to e raised to the power minus x sine of y I unit vector minus e raised to the power minus x cos of y j unit vector plus twice z, and we have k unit vector. Okay. So density is given in terms of the unit vector I, j and k. So it means this density is dependent upon our x, y and z basically. So we are going to use the differential form of the Gauss law. Okay. You can say differential form of Gauss law, which gives us that differential dot our flux density is equal to our density of a free space, charge density rather, and here this is our volume charge density. Rho is volume charge density, and the left side, this particular term, this is called as a divergence of vector field. This is called as a divergence of vector field, that is our D. Now we can easily find out the divergence of the vector field. Okay. And we can say, calculating the divergence. Calculate divergence of our flux density, and which gives us that the charge density is equal to partial derivative of density component wise. So this comes as partial derivative with respect to x, partial derivative with respect to y, and partial derivative with respect to z. And d is given to us. So this first vector is our d of x, second is our d of y, and third is our d of z. So we know that our d of x is equal to e raised to the power minus x sine of y. So its partial derivative with respect to x will be equal to minus e raised to the power minus x sine of y. Similarly, d of y is given to us minus e raised to the power minus x, and we have this as cos of y. So therefore partial derivative with respect to y will be equal to here, okay, in partial derivative, like it is with respect to x, then this second variable y we are going to treat at constant. Similarly, here it is with respect to y, so we are going to treat this x, that is here second variable, as a constant. So here we are going to derivate our cos of x, which is minus sine of x. This gives us e raised to the power minus x, and we get a sine of y. And finally, we have our d of z, which is twice z. So we get partial derivative of z with respect to z will be equal to 2. So we substitute, we get this as charge density, volume charge density is minus e of x minus of x sine of y plus e of minus x sine of y plus 2, which gives us, because these two terms cancel each other, we get this as 2 coulomb per meter cube. And we can also find out, or we can say, at origin, our x is equal to y is equal to z, all these are 0. Therefore, if we substitute this, our charge, volume charge density is equal to e raised to the power minus 0 sine of 0 plus e raised to the power 0 and sine of 0 plus 2. This also comes as 2 coulomb per meter cube. Now we are easily going to find out the total charge. Total charge enclosed in a small volume delta V. Enclosed in small volume delta V this gives us that the charge Q will be equal to charge density multiplied by small volume delta V. And this delta V is given to us as 2 into 10 raised to power minus 9 because it is incremental value. So volume, also increment volume. Okay, so the rate of change of volume in steps is increasing by this delta V. Now we we know our delta V, therefore we can say our charge Q will be equal to 2 into 2 into 10 raised to power minus 9, which gives us 4 into 10 raised to power minus 9, giving us 4 nano coulomb, which we were supposed to find out. So we got this as 4 nano coulomb. Next question. It says that if QF is the free charge of the capacitor plates and QB is the bound charge on the dielectric slab of the dielectric constant K placed between the capacitor plates, then the bound charge QB can be expressed as. Okay, I here forgot to put out the options, but we are going to find out the relationship between the bound charge and our free charge. That's a basic question here. Okay. And the bound charge is on the surface of dielectric and free charge is on the plates of the capacitor. And here we can say that we are having electric field within the plates that is with dielectric as well as without dielectric. Okay, we can just write it also. Okay, so we can say electric field without dielectric. Electric field without dielectric. So let us call this as E naught, which will be equal to our charge on the plates, that is QF, and we have epsilon naught times A. And this field is obviously between the plates of the capacitor. Next is electric field with dielectric. Electric field with dielectric. As soon as the dielectric inserted, we know, let us suppose that electric field is of E. Electric field get reduced by the amount of the dielectric constant. So we have this E naught. E naught is, we already know this will be our QF upon K A epsilon naught. Now we are going to find out the electric field due to bound charges alone, that is due to only the basic formula. Therefore we can write the electric field due to bound charges alone. And we know that the bound charges creates electric field which is opposed to the original electric field. If the bound charge electric field is given as our EB, then this EB will be equal to our E naught, that without dielectric, minus the electric field with dielectric, because they are both in opposite direction. We substitute their respective equations. We get this as Q of F upon epsilon naught A minus Q of F, sorry, this is F, Q of F, and we have here K epsilon naught A, and we can take Q of F epsilon naught A as common. We get this as 1 minus 1 upon K. And if the bound charges alone produces the electric field, that is our independent formula for our EB, So we can say bound surface charges produces field which we called as our EB. So we can say our EB will be charge bounded, and we have this epsilon naught times A, and we substitute in EB. So we get from here that our QB upon epsilon naught A is equal to QF epsilon naught A, and we have this as 1 minus 1 upon K. Here epsilon naught A, epsilon naught A cancels out. Therefore, we get our QB is equal to QF K minus 1 upon K. So this is the relationship between the charge on the plate and bounded charge on the our dielectric. Next question. It states that an electron with kinetic energy K1 enters between parallel plates of a capacitor at an angle of alpha with the plates. It leaves the plates at an angle of beta with kinetic energy K2. Then the ratio of kinetic energy K1 is to K2 will be. So we are given that we have a parallel plate capacitor, and the angle with respect to plates is incoming is alpha and outgoing is our beta. So let us draw the parallel plate capacitor, and suppose this is our parallel plate capacitor and it is entering at an angle of alpha, and we have this as a suppose positive and the other end will be our negative. So the electric field will be in the upward direction. And our charge enter at a electron enter a alpha with the plates. Okay. Suppose we are having a charge which is entering at an angle of alpha with the plates, and it is leaving with the angle of beta with the plates. So this is our incoming and this is our outgoing, and for the sake of convenience let us suppose that the incoming is our V1 and outgoing outgoing is our V2. So we can just, because the force is acting along, suppose this is our X and we have this is Y, so force will be applicable only in the Y direction. Okay, so if we divide the component V1 into two components, so we are going to have this as V1X and V1Y. Okay, and these are the velocity components of electron on entry. Velocity component of electron on entry. Similarly, we can write that our V2, it can divide into our X as well as our Y, and these are the velocity component on exit. Velocity component on exit. and our electric field is acting in y direction. Electric field is acting in y direction. So it means the force of this electric field will be only affecting our y component, that is our v2y as well as our v1y. So this component v2x and v1x is going to remain constant. It means horizontal velocity remain constant, same. Therefore we can say that electric field is acting in y direction, therefore no change in horizontal velocity. Or from here we can say that our v1x will be equal to v2x. Now we can just write this v1x and v2x in terms of the angle. So v2x will be giving us a v1 cos of alpha will be equal to v2 cos of beta. Let me draw it, it will be much more convenient. And we are having components of v, this will be alpha, so this will be our v1x which will be equal to a v1 cos of alpha, and this will be our v1y which will be v1 sin of alpha. And similarly for the other side also, we are going to have one second. Let me 1 second. Is it correct? v2 and this will be our v2x, and we are having this as v2y. Yeah, so v2x will be our v2 cos of beta, and v2y will be equal to v2 sin of beta. Yeah, this is correct. And we can easily find out the ratio v1 by v2. So we can say that our v1 upon v2 will be equal to cos of beta divided by cos of alpha. And we know that kinetic energy is equal to over half m v square. Therefore we can write this as k1 is equal to half m v1 square, and our k2 will be equal to half m V2 square. We need to find out the ratio. So we get our K1 upon K2 is equal to half m V1 square half m V2 square, and this half m cancels out. This comes as V1 square upon V2 square, which is our cos square beta, and we get this as cos square alpha. So this is the ratio of the cos square beta upon cos square alpha. Yeah, so option D is correct. Option D is correct. So this completes the 7th question from the year 2021, and in these first 4 parts, part 1, part 2, part 3 and part 4, we dealt with only the mains question. We are left with the advanced question, which we'll be covering in part 5. So this completes the part 4. Thank you.